All right. So it's my pleasure to have Binghui Peng presenting today at the RL Theory Seminar. He's going to talk about the complexity of non-stationary reinforcement learning. And Binghui is a student, a fifth and final year PhD student in the computer science department at Columbia, and he's advised by Christos Papadimitriou and Shi Chen. So previously, he obtained his bachelor degree from Tsinghua. He's broadly interested in theoretical computer science and machine learning. His research interests include the role of memory in learning, theoretical foundations of continual learning, and learning in games. And I guess at least two of these topics are going to be covered in today's talk. And before I forget, he's also on the job market. So if you have some cool faculty jobs that he might be interested in, please let him know. Binghui, stage is yours.
Yes, thank you very much. And thanks very much for the introduction and inviting me to present a talk here. It's my great pleasure to present our work on the complexity of non-stationary reinforcement learning. This is a joint work with Christos Papadimitriou. Okay, so we all witness like a huge success of reinforcement learning, and we view its empirical success in different domains, like Go's. This is some kind of board game, and Atari, and I think in recent years, this success has been witnessed for essentially all board game and video games. Also, there's some like ongoing efforts that many of you know may already aware, like some applications arise in control theory, like for robotics or autonomous driving car. And also more broadly, I will provide a general framework for study decision-making and applications in recommendation system, finance, and so on. So I'm saying this is as an ongoing effort because there exists some big achievement, but in order to deploy it in real life, they're still facing some challenges. For example, for robotics, sometimes the data where we still experience the lack of data for robotics. Well, for autonomous driving car, I think the current one is already pretty good, but at the end, we want the driving car should have a very good safety guarantees, and this also happens for other decision-making problems. Sometimes we have lack of data. Sometimes we just want the algorithm to be good and have formal guarantees on its performance. So yeah, so the empirical success is charming, but you probably most of the audience in this talk will do is like want to gain some theoretical understanding or at least some conceptual understanding of the success. So I think one major topic for this theoretical understanding is to try to understand the sample, the data, or computation efficiency. And another topic I'm caring more about for me is that the trustworthy of these decision-making algorithms. So we all know this performance of RL is amazing. Sometimes it should definitely surpass the behavior of humans. We witness this amazing performance. But how can we guarantee that this algorithm never make bad decisions? For board games like Go's, if it make bad decision, it's good. It's not at the end word because the worst outcome is that you lose a game. But if we really deploy this reinforced learning algorithm to real life, sometimes we want to make sure they're not making any bad decision. And I think this is one motivation I'm carrying about some theoretical result for reinforced learning. And yeah, and as I said, in real life, if we really want to deploy RL, we need to have some such guarantees. So let me just give a very, very brief introduction to RL, so to make sure everyone is on the same ground. So RL provides a general framework for study decision making, and typically it forms as a interaction between agents and the environment. So typically we study Markov decision process. There's a set of states set of action, and considering the finite planning horizon in this talk. And on each state, after taking action, we receive reward and transit to the next state. And our goal is to maximize the total reward over each steps. Okay, I'm talking about deployment of RL. So at the phase of deployment, the environment actually could undergo constantly change. So here, environment could have different meanings under different application scenario. For example, it could refer to nature. For example, probably the time, the temperature, or the circumference changes in the nature. And also, this environment could also involve other agents, probably other human or robotics. And this, human also makes decisions and change the environment you are playing with, and they also playing some RL algorithms. And finally, probably sometimes the rule can changes, and for example, for robotics, probably it will have more and more functions, and these are all like changes, environmental changes we need to take consideration into. And the automated dream I'm thinking of is like we want to build everlasting machines that can make decisions regardless of these environmental changes. Or in other words, it can quickly adapt to these environmental changes. And I think that's what this field of non-situational reinforced learning caring about. I will operate as a NSRL in the talk. And it's also known as, it's also has a very deep connection with other fields like continual RL or lifelong learning. And from my perspective, I think these are essentially the same. Okay, and I'll just use the word non-situational reinforced learning in the rest of the talk. Okay, so let me spend a few minutes, take a brief overview of the literature. So first, the reason that people care about this problem is that these classical approaches, for example, value iteration, policy gradient, does not generalize well to the non-stationary environment. It does not evasion update. For example, if I just make some simple changes to the underlying markup, the underlying MDP, then it's unclear how can you quickly update your value function or your policy. And as I'll mention soon, what people done is usually just relearn the optimal policy from scratch. But this is not what we want because the space is usually astronomical. Okay, so the problem of non-stationary reinforced learning is mostly studied in two frameworks. The first framework, I will call it the change detection framework, where the idea is to and where the focus is more on the statistical challenge, and the people want to figure out which part of the environment changes. And in order to detect these changes, people apply some statistics technique like change point detections or hypothesis testing in order to figure out the change. And the idea is that after you find the environmental changes, then what people do is just to recompute the policy. Okay. The second line of work, I'll call it a regret minimization framework, which tries to balance the between exploration and exploitation. And by now, there's a long line of work on this. And so let me just try to give a very high-level overview of what people did in under this framework. Some of the state-of-the-art algorithms just try to maintain multiple threads of MDP. Some of the MDPs are run for longer time, but some of them just restart quite frequently. And the reason that you need this restart some MDT algorithms frequently because if the environmental changes, you want to capture these changes. And the final algorithm kind of just switch between these different frequent MDP algorithms. And here people care about dynamic regret, and which is, I think, a notion borrowed from the online learning literature. I think probably the current state-of-art regret bounds. It's treated by the paper by Wei Luo in 2020, and also another group by Mao in 2021. So the dynamic regret bound is that s to the 1/3, a to the 1/3, delta to the 1/3, h times t to the 2/3. That's a total dynamic regret. And here, delta is a new parameter, and this typically refers to the variational budget of the underlying changes. In other words, it's just it measures the total change of MDP. So in different problem setup, this data could sometimes have quite different meanings, but from high level, just measure total change. For example, the L infinity norm of the reward change or the total number of times the environmental change. Okay, so in this work, our focus is mostly on the computation efficiency. So let me summarize the current approach. For change detection framework, what people do is if there's enough environmental change, then you just restart to learn the optimal policy of value function from scratch. For regression minimization approach, people maintain multiple threads, but they still try to frequently restart the MDP algorithm and see if the policy changes. So in summary, all this approach kind of suffer from computation inefficiency because they need to constantly restart the algorithms instead of probably changing smoothly your policy and your value function. And their computation cost roughly equal to the computation cost of a single MDP algorithm times the total changes. Okay. So that's kind of not what we exactly want, because we want, probably we want a more efficient update algorithm, such as if there's a small changes, then the runtime also do not and then it also does not cost too much computation cost. And at least we want to avoid a restart running a new MDP algorithms. But there's a lot of paper on this, but it seems this is a bottleneck, and the question we ask is kind of is this inherent? And so the major topic of this talk and our work is about the computation complexity of non-stationary reinforced learning. To summarize, we try to study is there any computation efficient way to handle non-stationary changes. Okay, let me state our result. So our main result is actually a computational hardness of non-stationary reinforced learning, and we prove this problem is kind of intractable. So here's an informal statement of our result. We prove, assuming the strong exponential time hypothesis, non-stationary reinforced learning requires roughly S times A times H amount time for each state action update. Let me parse the result. Okay. So in this talk, I will use little o1 notation in the exponent. I know sometimes it could be confusing, but it's quite common in the complexity literature. And if you're confused about it, think about it as 0.001. Okay, a tiny constant. So our result is based on the strong exponential time hypothesis, which I'll explain in more detail later. But for now, you can just imagine it as a strengthening of the classical P versus NP conjecture. And our algorithm says a non-stationary reinforced learning requires S times A times H amount times time for each state action update. I will formally define what's a state action update later. But from a high level, simply speaking, it's just we allow one single change for each update. That is, we allow the reward functions to change exactly for one state action pair between each update, and the transition kernel does not change. Okay, that's kind of the most simplest change I can imagine, because the change is done only 1 bit, costs you 1 bit, right? And our result showing a 1 bit change already costs you a large computation cost. Okay, and this S times A times H is roughly the computation cost of computing a coarse approximation of the value function. And this is kind of the time you relearn the optimal policy from scratch. The takeaway message here is that sometimes relearning from scratch is indeed necessary in the worst case scenario, and this could happen even for the simplest environment change. Okay. Oh, your question? Yeah.
Yeah, I guess maybe you'll talk about this, but are there examples when this worst case doesn't happen, and more benign cases? Is this really an MDP thing, or does it already happen in, let's say, shortest path problems? Or I don't know. I know nothing about this field, but it feels to me that, yeah, I don't know. I would want to know more about like in related problems that have additional structure.
Sure.
How much do we know about
Okay.
similar problems?
So in the next slides, I will talk some assumption can like circumvent this worst case difficulty. And in the later part of the talk, I will also talk about, what's the intuition of this difficulty. And
And then
I'll answer your question at
yeah,
that time.
okay.
Okay, cool. So so the next question we want to ask, there's a worst case barrier, but we all know that worst case barrier is not the end of the world, right? So we ask a question: when can we provably overcome this worst case barrier? So we provide the answer, but I think the answer is just a partial one, and I'm very interested if there are more like plausible assumptions that can circumvent this worst case barrier. So the assumption we make is kind of like by the assumption that the environment is expanding but not changing. What does I mean by expanding but not changing? So when we only have incremental update, that is the change of the MDP involves only the introduction of new actions, the new states, but we don't change the existing reward and the transition kernel. Okay. Under these circumstances, we can show some positive result. But let me first elaborate on why, what motivates me to think about this assumption. Clearly, I don't think this assumption holds for every application, but I think for applications that involves a lot of exploration and or the decision maker are equipped with more and more choices instead of these existing choices changes, then this assumption could hold. For example, if you go through a maze and you just explore the map and your choice become your available choice become more and more after exploration, but what you have will not change. That's just my high-level intuition on making this assumption. And with this assumption, and if we only assume there's an incremental update, we give a very simple algorithms, which we call like lazy Q-value iterations, that has amortized the runtime poly, H, or epsilon for each new state action pair. And yeah, please ask questions.
Glenn?
Right. So in the maze case, when you have a world state that is already known, policies that are already known, and then the world state expands, for instance, if you go back one slide, if you don't mind.
Sure.
You can learn about, so in the fog of war case, like as you've given here, you have the maze, you've got some element of the maze which isn't known, but everything else, there is a learned MDP. What happens if new information sort of reneges or comes into conflict with the existing information, even if it's just an expansion of the world space or the view, I suppose?
I think you need to formally define what you mean by conflicts. So does it change what's your existing state action pair, change the existing reward function or transition property? Or I think because most likely in this talk I will focus on this this most a standard and the simplest tabular cases. So I think what you said, I don't know what exactly means in tabular case, but I think this is a very interesting question if you goes beyond this tabular cases, right? But I think for tabular cases, I don't know how to formalize, your intuition here.
I'm struggling with that as well a little bit. A good example of this would be, we have a collection of policies that are finding routes through a maze that satisfy certain criteria. And we have certain routes through the maze, but it's incomplete. The maze is incomplete. We have certain routes through the maze, which one optimization would be least backtracking or fewest turns or what have you. And then new information comes in, we realize that 2 routes through the maze are actually a dead end, right? Like that eliminates that as a possible route through the entire maze. So it
good.
even
I
though
think
up
okay.
until that point,
Good.
those are high value. Suddenly
Yeah.
they become low value.
Yeah, good. I think in that case, it's kind of like goes back to my previous slides, at least in the tabular cases.
Yeah, like why is this an expansion? Like it feels to me that you are overwriting some information that you suppose was there,
Okay.
rather than adding state or adding an action here.
I think, for example, let's say previously you go to a crossword, but you only have the option of go right and go straight. But later, maybe some other like event, I don't know, something changes. Now you can go right, so you have more options. That's what I'm thinking of. Okay, I mean, again, I think this part is I like to involve more discussion. Okay, I'm also not exactly sure what's the right assumption to make, but that's one assumption I can think of. Okay.
Oh, I see. So when you speak of expansion, you mean like if the entire set of available options has a completely new chain or an entirely new sort of a branch.
Yeah, I think I'm thinking more. Okay, you have more options, you have more choices, and things like that. Okay.
You introduce a new state, but you may not want to go there, or you may want to go there, but it doesn't interfere whether what you computed before was valid or not, right? Like everything that you computed before was correct. It interferes with what's optimal, what's not optimal. Maybe a new shortcut arises. If no new shortcut arises, then this is a trivial thing, right? Like you're just happy with what you had before. So you just have to change. You have to check whether you have a new shortcut.
Okay. Yeah.
That does influence prior assumptions about the way the problem space expands, doesn't it? I think this is possibly grounds for like a separate discussion towards the end. Yeah, sorry to kind of sidetrack there.
Yeah. Thanks for the question. Okay. Shall I continue? Okay. Good.
Please do. Sorry.
Thank you. Thanks for the question. So let me try to make sure. Okay. So that's the statement of tone, and I think I believe this is just a partial answer. So I will ask if in the future see more plausible assumptions. Okay. Okay, in the talk, I will actually most focus on this hardness result. I will start by explaining what's like strong exponential time hypothesis, why this is necessary, and why we should, why it yields our algorithms, and then I'll talk about how we derive the hardness result. Cool. So computation complexity. The conventional wisdom of computation complexity, at least before the year of 2010s. So when we suspect a problem, it's hard. And we spend a lot of time trying to find polynomial time for it, but we do not succeed. Then what we should is we should prove it's NP hard. So probably there's some inherent reason why we cannot find such good algorithms. So now think about non-stationary reinforcement learning. Previous works try, I also try, but we don't find good algorithms. We suspect it's inefficient because we suspect maybe under very simple change we need to just restart computing the policy again. But unfortunately, not unfortunately, but at the same time, it also admits a trivial polynomial time solution, right? I mean, at least after each change, you can just relearn the optimal policy of function, value function from scratch with which costs a lot, but it's also in polynomial time, right? So in other words, the cost is expensive because we learn from scratch expensive, but it's still in polynomial time. So for this case, the P versus NP conjecture does not help us because there exists polynomial time, so we can now prove non-stationary reinforcement learning. It's NP hard, so it's obviously not. So we can now kind of based on this conjecture, and why I refer you to an excellent survey by Virginia Williams on this fine-grained complexity, and she explained very well why traditional P versus P conjecture does not help us in this regime. Okay, for fine-grained complexity, to understand the underlying logic, let's go back to the definition of NP, non-determinate polynomial time. So we know that the problem of set is the simplest and earliest problem to be shown to be NP complete. For those who don't know set is just a system of discrete equations that involves negation, conjugation, and so on. Okay, the P versus NP conjecture says there's no polynomial time outcomes for solving set. And okay, now if we have a problem and we find it's hard, we can just show it's NP hard. And by showing this NP hard, it means there's a polynomial time reduction from the problem of set to the problem of gamma you care about. By showing this NP hard, we can conclude gamma does not have polynomial time outcomes unless under the assumption of P versus P not equal to NP. Okay, that's the case when we suspect a problem has no polynomial time solution. The strong exponential time hypothesis is a strengthening of this P versus NP conjecture, and it's a at least widely studied conjecture that people have tried, but it's not great for so many years. And the conjecture states that for any epsilon, there exists a case such as k set cannot be solved in time 2 to the 1 minus epsilon times n. Here, k is a parameter that depends on epsilon, and k set means each clock consists of only k variables. So this is indeed a strengthening of the P not in P conjecture, because the conjecture, this STH, says that set cannot be solved in less than exponential time. Okay. So this is this called I will break as STH. It is a central conjecture in the field of fine-grained complexity, and also I'll tell you very soon it yields many fine-grained polynomial lower bound. Okay, but before that, we need to re-examine the definition of reduction. So in order to we need to perform some fine-grained reduction. This is essentially the same as this classical Karp and Lavin reduction. But when you use this fine-grained complexity, usually we need to track carefully about the reduction time. And sometimes the reduction time can be exponential because our base assumption is exponential time assumption. Okay. And I just want to mention, I personally believe this fine-grained complexity is probably the most exciting recent development in complexity theory. And this is still a very active research area. And it has many applications. And using this fine-grained complexity, for example, STH, we can now prove polynomial lower bound for Algorithmic sync problems. For example, orthogonal vectors, nearness neighbor, eddy distance. So in this work, we applied it to the problem of non-stationary reinforcement learning and show some fine-grained lower bound. Okay. Now for the hardness of non-stationary reinforcement learning, let me first just give a formal definition of the setup we consider, so make sure we're on the same pages. The sequence of T update, and we consider the finite planning horizontal H. The state, action, transition kernel is assumed to be fixed. The only changing part is the reward function. And at each update, I call it a state action update. The transition kernel and the reward function stay the same, except one state action pair. For that state action pair, transition kernel stay the same, but the reward would change. Okay. And our final goal is only to output the value at the initial state. Okay. Okay, let me just end. Okay. What was the question here?
Also, just a simple question. So here, the update, do you mean to compare with existing literature? They use T, but you use T plus 1?
Sorry, what was T and T plus 1?
Yeah, you mentioned the state action update. Is it to compare with the existing literature?
Literature?
Well, I think it's like the reward changes, like the so fifth bullet, 1, 2, 3, fourth bullet point, the reward changes from RT to RT plus 1. So I don't know, the question is about this change or indexing. Yeah, I guess that is the question.
Okay,
yeah. So let me just explain. So between the the T stop date and T plus 1 stop date, the only change is only one state action pair, and the reward changes. Okay, that's the change.
Okay.
So it essentially just one bit or like log bits change. Okay.
Yeah, I'm a little bit okay. So you probably said this, but what's the value that you're trying to compute?
Oh, okay. It's the value of the optimal policy. Okay.
Is the optimal policy allowed to change by time?
Yes, I think if you change the rewards, the optimal policy would change. And here I'm only ask you to output the probably just the v value or the the value of the optimal policy at the initial state.
Is this for every single time step?
Yeah, every single time step. Yeah.
Okay.
Oh,
Okay. So it's like it would be sufficient to consider a single change or something like,
Yeah,
right? So you're given an MDP, and then suddenly someone says that, oh, by the way, at this state action pair, the reward just got a new value. Give me the value of the initial state, and you're asking how much compute time do I need to spend on this?
Exactly.
Okay.
So I
it's
think
like the capital T is irrelevant. Like we don't care about capital T.
Yeah.
Okay.
So yeah, it's I'm not saying like in real world non-reinforcement learning look like this, but this is kind of the simplest task you can imagine. Right? One bit change and ask you the value at the initial state. Okay. Good. Yeah. So let me just first continue to talk. Okay. So let me show you the formal statement of our result. Again, I'll use little one in the exponent, but take it as a tiny constant. Our result formally states that unless strong exponential time hypothesis is false, there's no algorithm with amortized runtime SAH to the 0.99 can approximate the optimal value of a non-stationary MDP. In particular, anytime with better runtime fails to distinguish between the following two cases. In the first case, the optimal policy has value at least h/4 at some round. Okay, there's some round that have very large, value, have larger reward. In the other cases, over all rounds, the value of the optimal policy is very small, less than h/100. Okay, that's statement. That's in this talk, I'm stating our result like by considering non-stationary RL that only have reward changes. You can imagine this result like just quite robust and holds for transition kernels, extend to infinite horizon MDP, and also it holds like there's only tiny fraction of states are changes. Question, yeah.
So capital T needs to be large, can be 2. What is going on with capital T?
Okay, so capital T, we assume it's like a polynomially bounded, so not super large. It's not exponential, okay, in terms of ISA and H.
But it's okay. So
it could be small, but it cannot be too large.
It's really important that capital T is not just a constant.
Yeah. It holds like for like until like, for example, T equal to S times H to the like 100 or something.
So, but if capital T was just a constant, like why would that be? Like, what's your conjecture? Like,
oh, okay. I think our result hold for T equal to constant, but I'm saying like it does not hold if T is exponential. Okay.
Sure.
Because if T is exponential, it kind of like
the result seems to be stronger if T is a constant.
Yeah. I think this result hold for T equal to constant. Yeah.
But T has to be at least some number, or can it be just like 2?
Yeah, it can be 2. Yeah.
Okay. So, all right. Okay. Just take T equals 2.
Sorry. Yeah. Any concentration.
P equals 2 is game. All right.
Yeah.
That's the simplest and strongest case.
Yeah. Okay.
Okay.
Okay. Cool. So now I will try to explain how we execute the reduction and what's kind of intuition behind this hardness. I will use the reduct from the following intermediate problem, which is so-called the maximum inner product problem. In this problem, let n be a input parameter, and m be some parameter that's of roughly like n to the 0.001. Okay, and w is some like parameter that's that's less than n to the 0.001, greater than some like arbitrary polynomial. Sorry, arbitrary polylog. And okay, so the problem maximum inner product. The input is two collection of sets. The first collection of set is B, B1, B2 to Bn. And the second collection of set is C, C1, C2 to Cn. And each Bi, Cj is a set, it's a subset defined over the universe of M. And the cardinality of C is much smaller than B. Okay. And the task is to distinguish the following two cases. In the yes instance, there exist two sets B and C, such as C is a strictly subset of B. Okay. While in the no instance, for every set B and C, the intersection of B and C is much smaller than the cardinality of C. So again, yes instance, there exists a pair such as C is a subset of B. In the no instance, the intersection for all pair is just small.
So you could rephrase it like that. In the yes instance, the intersection is C, like has the cardinality of C.
Yes,
in the no instance, it's much smaller.
Yes.
Okay.
And
it cannot be possible that both yes and no hold because W is greater than 1. Answering the use question.
Okay. And okay. We built on this beautiful result on Bond, Rubinstein, and Williams, which I found is very beautiful, and I think it's very important result. Okay, they prove assuming strong exponential time hypothesis, no algorithm can solve max IP in sub-corrected time. Okay, recall if you have corrected time, then the problem there's a trivial solution. You just consider every pair, right? But this result is very strong, and they say that assuming a strong exponential time hypothesis, you cannot solve max IP in sub-corrected time. Okay.
Okay. So now I have a few questions about this.
Okay.
Why is this called maximum inner product?
It's a contained, whether B and C is contained in each other. It's kind of like an inner product. Okay.
Okay. It's like the intersect. It's like binary vectors.
Yeah. It's actually, in the original paper, it's like a bichromatic maximum inner product. So bichromatic means 0, 1. Okay. Yeah.
And then the other is like, how big is this W exactly? It's like this 2 to the log n, blah, blah. Okay, so how do I think about this? This is like...
for example, think of this W be 2 to the square root log n. Okay.
Yeah, I was thinking about like 2 to the square root log n would be a good example, right?
Yes.
So it's not like n, but it's like, okay, growing, but okay. It's like these fine distinctions are quite hard for me. Okay.
Okay, good. Yeah, I think personally, this is a very strong result. Essentially, our work just built on it. Okay. Now let me explain the reduction, and let me first explain the intuition. Okay. As I will explain later, max IP captured the challenge of the reachability problem. Well, for non-stationary reinforcement learning or even reinforcement learning, we need to solve certain reachability problems. Okay, so this will make the hardness of max IP will imply the hardness of non-stationary RL. So let me just spend a few words on the reduction. You may notice that this max IP is a stationary problem. What I mean by stationary problem is that the input is given, no update, right? Well, non-stationary reinforced learning is a called dynamic problem. There's some update to it. So when we do the reduction, we just construct a sequence of updates for non-stationary reinforced learning, such that if there exists an algorithm that's solving all of them, like gives answer the initial value, answer the value of the initial state at each step, then aggregating these answers will resolve max IP. Okay, that's the idea for reduction. And the reduction is actually quite simple. I mean, that this conceptually is quite simple. I will start from a weaker hardness result that hold even for planning horizon equal to 3. You can say like for if h equal to 2, trivial algorithm exists, but I'll show you even for h equal to 3, there already exists some hardness results. Okay, let me show the reduction, but let's first recap the parameter. So in the max IP, there's like a 2 parameter n. M is the universe size, which roughly n to the 0.001. And I will construct an MPP that has 3 layers: the state and action. The size is both of them of size n, and the total number of the update is 2mn. Okay, there's a initial state. In the first step, let's just assume it's just a single initial state. Okay, in the second layer, there are n state. In the third layer, there are m state. That's just correspond to the element of the ground universe. Okay. In the initial state, I assume there are n actions. Okay, and the ith action will direct the initial state to the ith state in the second layer. For the state in the second layer, I only assume it has 1 action, and this action will route uniformly at random to the bith state in the third layer. In particular, for the first state, it has 1 action. The action will route you uniformly at random to the state in B1. As I said, you can view the state in the third layer as element from the ground side. There's 1 action per state, and for example, for the last state, it routes you uniformly at random to state in Bn. Okay. And let's assume the reward in the first 2 steps are always 0. And the reward in the last step initially is also 0. Okay, this is the case for round 0. In the first m or 2m update, I will increase the reward for state in the third step. In the third layer, and I will increase it according to the set C1. Okay, here, for example, suppose C1 equal to 1 and 2. Then in the first 2m update, I will increase the state action, the state value of the first and the second state in the third layer to be 1. Others keep the same. Okay. This is first update. This is the first 2m update. I'll continue, and from the 2m plus 1 to 4m's update, let's assume C2 equal to 1m. Then I will first decrease the state, the reward of each state to be 0 in the third layer, and then I will increase the states that's inside of set C2. That is the first state and the last state. Okay. I will repeat this process for roughly 2 times m times n steps. Okay. Now let's show the analysis. Quite simple. It's without loss of generality, to assume the set of B and C have equal size, and C is much smaller than B. Okay. Recall, like in the problem max IP, we need to distinguish that case like some set C there's a pair C like C J and Bi, such as say J belong to Bi, and the case that all the interaction between each pair is quite small. Okay. In the yes instance, suppose Cj is a subset of Bi. Then I claim the optimal value equals to C over B at around 2j times m. The reason is simple. You just consider policy that chooses Aj at the initial state. Okay, if you choose Aj, then it will direct you to the J state at the second layer, and then you just choose the action at that state. It will direct you uniformly at random to state in bi, right? But we know that the intersection of bi and cj is of size c. So the optimal value here equals to c over b. Okay, and actually here, for no instance, okay, that is the intersection of every pair is quite small. Then we can show the optimal value is at most c over w over b for all rounds. Okay, the reason is kind of similar. And let's see what it implies for non-superficial reinforced learning. It says like max IP, we start from the theorem that says max IP requires n squared time. Then this means, this means like non-superficial reinforced learning also requires n squared, roughly n squared time over t updates, because if you can solve non-superficial reinforcement learning, if you can solve non-stationary reinforced learning in less time, you will be able to solve max IP in less time. And then the amortized time is just the total computation cost over each update. So it's n squared over t, which is roughly of like n, and n is roughly of size s. Okay, so this already gives you a strong lower bound. And there's one problem if you care about approximation. Okay, the problem here, the optimal policy itself has very small value. Even in the yes case, the value is c over b, which is if you plug in this parameter, which is roughly s to the minus like 0.01, which is a quite small number. And this is okay. If someone tells me like, okay, I only care about additive like constant approximation. For example, I only want to have a like 0.1 approximation to the value, then our lower bound does not rule out this possibility. So in the next slides, I will show how to amplify this gap and improve the optimal value. In particular, we want to amplify the optimal value to roughly of order h, and we want to keep the gap between the yes and no instance. I recall in our final statement, the final gap is in the yes instance h over 4. In no instance, the value is h over 100. Okay, let me present some high-level idea here. The idea is actually, again, quite simple. So you just construct roughly, now you need more layers, and you roughly construct M over C layers of this basic instance. And you recall in our previous construction, states, it's good. It has high reward, meaning that we assign reward 1 to it. But now, for those high reward states, I will just attach a chain to it, and it has reward roughly h. Well, for those states has 0 reward in the previous construction, I will just move to the next layer, and we roughly have like n to the 0.001 layers. Okay, question.
Yeah, just a quick clarification question. So do you really mean that you're going outside of the range of the 0-1 interval for the rewards?
So sorry. Can you repeat the question?
So if you are free to scale the rewards...
Oh, no, so sorry. Here I'm not scaling. Okay.
Okay, you are adding a lot of steps.
Yeah, I'm logging.
You have a reward of 1. And that's how you get this h.
You're
scaling the horizon. Okay.
Yes.
The horizon before was small. Now you need to change the horizon to be large. Okay.
Yes.
Okay. Got it. So then, yeah, okay. So the hardness partly comes from, in the additive case, of having a large horizon.
Yeah. Yes.
I see.
So so sorry. I think there are some typos in my slide. So here you should be replaced M over C with B over C. But but the idea is so let me just give you a quick explanation on why this amplifies the gap. Okay. So recall in our construction, in our previous construction, we say like in the yes instance with probability B over C. C over B, you will reach to a high reward state. So for each layer, you have probability C over B to reach to a high reward layer, and you repeat it roughly over for like B over C steps. So in a yes instance, the final reward should be roughly a theta h. Well, in the no yes instance, the previous the probability of reaching a high reward state is much smaller. Okay, and even if you just repeat it for many times, it's still going to be smaller and sublinear in h. That's a rough intuition, and let me show you the rough construction. So this is our previous construction, consists of 3 layers, and the idea is just we stack more and more layers to it. And now for states in the third step, it has some options to just go to the next layer, and also some options to go to a long chain. Okay. And okay, and the construction is similar. So roughly in the first 2 M rounds, I will just assign high reward to the chain of the first and the second state if C1 equal 1 and 2, and the others just have reward 0. I will keep doing this, and suppose C2 equal to 2 and M, then I will just change the reward of the chain of 2 and M, and so on. Okay, this is the last technical slide in this talk. So far, we have proved the amortized lower bound of roughly S to the 0.99 for a sequence of T updates, and T here roughly equal to S for the 0.99. Okay. So we want to improve the lower bound. Recall in our theorem statement, the lower bound is actually S times A times H, and it's holds for arbitrary polynomial length sequence. I will only sketch the high-level idea here. Okay. So we just to improve the lower bound, we kind of just need to slightly redesign this MTP and spread this state action pair over all steps and states. In previous construction, it's kind of quite imbalanced because at the initial state there are n actions. Well, for state in the second layer, it only has 1 action. We just kind of rebalance this. And for the second issues, in order to generalize to poly-length sequence, we kind of use the self-reducibility of the max IP problem. That's to say, we can split max IP into 4 instances. Recall previously we have a set of a collection of sets B and a collection of sets C. We can just split B into 2 parts and C into 2 parts, and run a max IP algorithm between each pair. So if we have a hard lower bound for the larger instance, we also have a lower bound for the smaller instance, as long as we only run this process for constant number of times. And this can improve this sequence length. Okay, sorry, this side is very rough, but conceptually it's just very simple. Do some optimization to the parameters. Now let me wrap up the talk. So what we show is that the non-stationary reinforcement learning is computationally intractable in the worst case, and unless you make some assumption, and one assumption is if you only add new actions and states. So what should we take from a worst case barrier? So we all know that if you play a worst case barrier, probably it does not really in real world application it's not exactly the case. For example, 30 years ago, we know optimize a neural network is actually NP hard. But now we all know that for most data set, you just run gradient descent over a neural network, you'll probably obtain very good performance. So what should we take from this worst case barrier? The first, I think, for all this theoretical work and also practical work I wear in the field of continual reinforcement learning, all of them are kind of doing something like restarting the policy from scratch. If you can, so this is kind of aligned with observation. And also, I think the method I'm taking from here is okay, if we really want to deploy non-stationary reinforcement algorithm to the real world, we need to be cautious, because if the algorithm is just too efficient, okay, in sometimes, then it would make bad decisions for real life decision-making problem. And if you look at the statement of our theorem actually indicates that if the algorithm just have small update time, then it just fails to distinguish between the case that there exists very good policy, or there exists or all the policies are very bad. So if you do not have enough runtime, then you cannot just distinguish it. Okay, this is, I believe, is kind of different from this neural network scenario, because for neural network, okay, there's an NP hardness result, but I just run gradient descent. It obtained very good objective value, so I know I succeed. But here, if you do not take enough long enough time, then probably you just find a very bad policy, but you just cannot tell whether it is a good policy unless you learn from scratch. I think again probably in real life there are more like structures, but I'm seeing as a like an alarming sign. Okay, and second, I think I hope this could be provide some insight for the difficulty of RL. For example, I believe that this reachability is some kind of difficulty of this problem. Let me just briefly summarize the future directions. And the first, I think, our algorithm uses fine-grained complexity to show some hardness for some RL problem. And I think, I believe this could be useful for other problems. I see some examples in of using fine-grained complexity by proving like an exponential lower bound for linear MDP and also for partially quasi-polynomial lower bound for partially observable MDP. But I think probably it will have more application, especially if you think about problem for a long time, or you do not think it's probably there exists some worst case barrier from fine-grained complexity. Also, another interesting thing to see is that any other like structural plausible assumption that circumvent this worst case barrier. And finally, I think typically in this field, people also not just consider tabular setting, but also consider like function approximation or multi-agent setting, and things you can also explore in this direction. And I'll wrap the talk here, and thanks very much for attending this talk.
Thank you. We do have questions. Okay, let me see. How do I see the hands? Someone raised the hand. Anyways, if you have a question, because I can't see who raised the hand, go ahead. All right, maybe that was an accident. I had a very quick question, which was that, do I understand correctly that in this construction, everything is deterministic?
So sorry. In the
construction that you have,
no.
Is there any stochasticity?
Okay, I think there's some stochastic like.
Okay, I missed
so,
that.
So okay.
I really have to think more about this.
So here, this action B will here I'm, for example, look at state the first state in the second layer. It only has one action, and this action will goes uniformly to.
I see.
I think too much. It's possible like we can remove some randomness, but I'm not sure here.
Yeah. The follow-up question to that was, is there a similar hardness result for the deterministic case, or in the deterministic case, actually you can do things fast? Is it inherently because the transitions are stochastic?
I think if it's really deterministic, I think probably it's more similar to some like a shortest path problem.
It is a shortest path problem. And it's like an acyclic shortest path problem. So you do know exactly what you need to do. So if there is a change somewhere, then you are propagating back.
Not exactly sure.
But maybe you have to touch everything anyways.
Yeah. I think it's possible that there's like some algorithms, not the super efficient algorithms. For example, if you think of this S and A roughly equal to of same size, maybe N. So probably, if S times A, for example, if S and A roughly equal to of the same size and they are equal to N, then probably the naive thing is like N squared time, but probably you can do better, like N to 1.5 something. I need to look at literature. I think there's some literature in.
There is literature on incremental computation of shortest paths. but I don't remember the details. It was a long time ago I looked at it.
I think it's only like incremental. Probably things will be easier. But here I think we allow arbitrary change. So,
I mean, incremental, usually they mean if you're in the shortest path problem that either you remove a node or you add an edge or remove
I
an
see.
edge.
Yeah. Then I think there's some literature.
Yeah. That's what they're looking at. But right, other related questions. So there is a particle way of like in these examples, the size of the state is the same as size of the actions in sense of force. Then H gets scarce, T gets scaled. So if you only have two actions,
I think in our final construction that doesn't matter. Okay.
You can somehow kind
I
of
think
just emulate
that
the
doesn't
n
matter.
actions with just two actions.
Yeah, 2 or
So
3.
that
I think
answers
that's
that.
enough. Yeah.
But it seems like at the beginning I was asking about whether t equals 2 is enough, but it seems t equals 2 is not going to cut.
Okay. Actually, I think the problem is, okay, if you have a like n update and it costs you like n squared time, right? Then I prove that okay, amortized time. So average step for the average cost for each step is n. This means at least some step takes your n step, right?
I got it.
So if you only have 1 or 2, like for example, if your t only equals to 1, so I mean, I think the longer the problem become easier actually. So for algorithm design.
Explain.
For example, if I have a very good algorithm that works when t equal to 1, right? I can just keep repeating these algorithms for n times.
Right.
And it gives me an algorithm that's for longer sequence, and the average computation cost is similar. It's the same, right? So I prove a hardness for when t equal to n, so it implies a hardness for t equal to 1.
Right.
But it does not imply like a hardness for t even longer.
Right.
Because it kind of the situation is if t is larger, then probably you kind of do some amortized thing. So sometimes you pay large, sometimes you pay low cost. Average, you are good.
Right. You can somehow think about the average MDP that you're getting and just solve that, and then I don't know, but like it depends on how much variability you can induce in the values along the way. Okay, got it. Very interesting. And if we keep the horizon small, let's say it's a constant, and we care about additive.
Yeah, I think that's a good question. I don't know the answer.
Okay.
I haven't seen thought too much, but yeah, I think that's probably need at least some new idea for our construction, some new things. Yeah.
Pretty cool.
Sorry, I don't mean to interrupt, but I have an unrelated question, if that's okay.
Yeah,
Absolutely.
sure.
So at the beginning, Chaba said that you were interested in multi-agent settings, and I was curious what model of game you've studied using this non-stationary RL paradigm. Like, was it Markov games or was it kind of stateless games, normal form?
I think I mentioned this non-stationary RL at the very end. I think probably there's already some work on this topic. I forgot. I can send you a reference afterwards. I'm not exactly sure, but I think probably assume there's a. You can also assume there's a utility, this reward in the game changes, something like that.
Well, I meant, did you have any work yourself in the multi-agent setting?
Sorry, did what?
Do you have like past papers in the multi-agent setting yourself?
I don't have a paper in multi-agent RL, I think. Yeah.
Okay, because I guess Christos has some papers about like the complexity of equilibrium and stuff like that, and this seems quite interesting for a learning agent in the game. But anyway, yeah, thank you very much. Great talk.
Yeah.
Any other questions? Z, do you want to ask? Okay. Regarding these alternative assumptions that could circumvent the worst case barrier. So what if the change to the reward is somehow limited in magnitude?
Sorry, what do you mean? So you mean some small like magnitude?
Data, yeah.
I think our change is like very local, right? But if you restrict, okay, if the magnitude is small, then I think naively, if the magnitude is less than 1/h, then you don't need to update anything, right?
But if that adds up over time, then eventually you need to update. So it's like
but yes. But I think that the problem is, okay, if it's too small, I mean, if the total magnitude change is too small, then you don't need to update. If it's large, then you solve a result, you need to update.
Right.
In some sense, yeah. Yeah.
There is some interesting regime in between.
I think I think
the boundary between like, oh, this is trivial.
I think it depends, how much you care about this dependence on age. Because I said, if the cumulative changes less than 1/h, then probably it's the total change is small. But if the magnitude is 1, it's hard. So it depends on how much you care about the dependence on age, I guess, right? Less than 1/h, trivial, don't need to change. 1, you need to change, and hard. Yeah.
There's a lot of things in between 1/h and 1.
Yes. But I think the problem is naive algorithms. Every time you observe the magnitude, it's like exists 1/h. You just can do some restart or kind of thing. So the overhead is h. So yeah, I think it really depends on if you want to like pin down the exact computation complexity, or you have a rough idea, it's good. Yeah.
Because the reason I'm asking is because I think that that's somehow the underlying assumption for many of the practical algorithms that people are designing, where you're kind of tracking changes, that it's by and large they are going to make some assumption about that the changes are small, so that the impact of the changes is small. Therefore, these incremental updates are not horribly wrong.
Yeah.
Or not for long, horribly wrong, and you can keep up with the changes. At least you can think about it like that. It's like what if you change the transition structure and not the reward? You can probably simulate the reward changes.
Yeah, I think transition
Even harder.
Yeah, even harder. Yeah.
Cool. Well, very nice work. Thank you.
Thank you. Yes, thanks for leading the discussion. Yeah.
I guess I stopped the recording.
And yeah, thanks everyone for coming.